Hello everyone, we are continuing the topic of MOSFETs. We are going to look at their IV characteristic equation and solve MOSFET circuits. So we saw two types of MOSFET transistors. This is the circuit symbol and the current and voltage labeling of an NMOS, and this is the circuit symbol and the current and voltage labeling for a PMOS transistor. So for an NMOS transistor, PMOS and NMOS equations are similar. We have an important term called overdrive voltage. It's defined as VGS minus VTN. For the case of NMOS, this subscript here represent the threshold voltage in an NMOS transistor. So when the transistor is in cutoff, V overdrive is less than 0. When it is in the triad region, overdrive voltage is greater than 0, but drain to source voltage is less than V overdrive, and this is the current equation, ID equation, that we're going to use for the operation of MOSFET in the triad region. When it is in the saturation, V overdrive is greater than 0, also drain to source voltage is greater than V overdrive. And here's the equation that we're going to use to solve the MOSFET in the saturation region or find ID. This lambda term is the channel length modulation factor. It's usually a small number, and that's equal to 1 over VA. This is VA is the early voltage, and it's usually a very large number. So sometimes in the problems we're asked to assume a 0 value for lambda, which is going to simplify the calculations. For the case of PMOS, we're going to use VSG instead of VGS because VSG is positive, and we're going to use threshold voltage with in an absolute value. We're going to use V sub TP, threshold voltage for a PMOS with an absolute value, because threshold value for a PMOS transistor is a negative value. So if it is in cutoff region, overdrive voltage is less than or equal to 0. When it goes in the triad mode, overdrive voltage is greater than 0. Also, voltage of source to drain is less than or equal to V overdrive. Again, we are using V sub SD instead of V sub DS for the case of PMOS, because voltage from source to drain is going to have a positive value. So there you go. I have an equation that relates ID to VSD for the case of PMOS, and if it is in the saturation region, V overdrive voltage is greater than 0. Also, source to drain voltage is greater than V overdrive, and that's my equation for the case of saturation region. Again, lambda, sometimes we're asked to assume a 0 value for lambda. So in MOSFET, similar to the situation that we had with BJTs, the gate to source voltage or V overdrive controls the value of ID and VDS. So the gate to source circuit is the controlling part, and this is the value of VGS controls ID and VDS. So, as for the purpose of solving the BJTs MOSFET circuits, we're going to have a similar approach that we had for BJT problems. We're going to assume a particular state for MOSFET transistors using the IV equations, the characteristic IV equations, and we're going to, after solving the circuit, we're going to validate our assumptions. The good news is that because IG is equal to 0, gate current is equal to 0 in MOSFETs, it simplifies the calculations. However, for the case of MOS operating in the triad region, the IV equation is a quadratic equation, so it's better to assume a saturation region first, and then if it is not in the saturation region, we need to go and solve this quadratic equation by assuming a triad region for the MOSFET. Let's look at a circuit problem. In this problem, RD is equal to 1K, VDD is 12 volts, and the goal is to find V out when the value of VI is 0 volts and 6 volts. So the parameters of the transistors are given, and threshold voltage is given, and the lambda is we're asked to assume about 0 value for lambda. So let's write the gate to source KVL. Let me label it. Voltage of gate to source is here. Voltage of drain to source is here. And this is an NMOS transistor because by just looking at the direction of arrow that's pointing outside, it's on the source terminal, and the arrow points outside, so I know that it's an NMOS transistor. So let me write the gate to source KVL. From there I have VI is equal to voltage of gate to source. Good. Then I'm going to write drain to source KVL. From there I have VDD equals to, so I have a situation like this. This is plus minus, this is my ground node. This is VDD. From this node to the ground node, I have a voltage equal to VDD. So VDD equals to RD times ID, and the current flows in this direction. This is my I drain, and plus V drain to source. That's it. That's my KVL for drain to source. I have 12 volts equals to 1K multiplied by I drain plus voltage of drain to source. So with VI equal to 0 volt, then I have from gate to source KVL, I have VGS equal to 0 volt, and I need to compare VGS with the threshold voltage and see if VGS is greater than V threshold or not. If it is greater than V threshold, then the transistor is not in cutoff, but if it is less than VT, then the transistor is in cutoff mode. So this is less than V threshold equal to 2 volts. From there, I know that my MOSFET is in cutoff. So from there, I know that ID is equal to 0. When the transistor is in cutoff, drain current is equal to 0. Then I have to find, the goal is to find the output voltage. V out is equal to V drain to source. Just by looking at it, V out is connected to the, I'm taking the output voltage from the drain terminal of this transistor. So V out is equal to V of drain to source. Then that is from the drain to source KVL, I can calculate this value of VDS. 12 equals to 1K multiplied by 0 plus V of drain to source. That is going to give me V out of 12 volts. Let's find the value of output voltage for the case of input voltage being equal to 6 volts. So again, I have a from gate to source KVL, I have VI equals to voltage of gate to source. From there, I have VGS of 2 volts, which is 6 volts. That is greater than V threshold, which is 2 volts. From there, I know that MOSFET is not in cutoff. Okay, so I'm going by the assumption, moving on by the assumption of this MOSFET operating in the saturation region. So voltage of overdrive voltage equals to voltage between gate to source, from gate to source minus V threshold, that's going to be equal to 4 volts. If by assuming that the operation is in the MOSFET operates in the saturation region, assume saturation, then I have that means voltage, I need to make sure that voltage of drain to source is greater than V overdrive, which is 4 volts. Also, I can use this equation for the case for ID when the MOSFET is in the saturation region. It's equal to 1/2 and W over L multiplied by overdrive voltage to the power of 2. So I have all these values for these parameters, and then I'm going to plug them in this equation and calculate the value of ID. Plus multiplied by 4 to the power of 2. From there, the value of ID is equal to 4 milliamps. Now, I'm going to use this ID in the drain source KVL equation to find the value of voltage of drain to source. So 12 equals to 1K multiplied by 4 milliamps plus voltage of drain to source. From there, V out, which is voltage of drain to source, equals to 8 volts. Okay, so let's check and compare this VDS with the value of V overdrive and see if our assumption was correct or not. Yes, this is greater than 4 volts. That means our assumption was correct. Okay, so ID is equal to, for this transistor circuit, ID is equal to 4 milliamps, and voltage of VDS or output voltage is going to be equal to 8 volts.